These two yesterday, if you've got a fraction and the numerator is held constant and the denominator is either forced to get really, really huge towards infinity or really, really tiny towards negative infinity, in both cases the answer would be 0. And then we're going to do an example or two where we'll try to use those. And I just wanted to let you know that just like last year, if you can do these, well, I guess there's a variety of ways you could do these. If this were a multiple choice scenario, if you can use the old pre-calc trick with degrees and all that stuff, you're welcome to use that. So can I show you a couple of different ways we could do this? So just so you know, this is all the same stuff, but here's a couple of different ways. So number one, you could look at it and say, hey, it's the limit as x goes to infinity, and so that means it's the right edge of the graph, way on the far right edge of the graph, and so I want to use the pre-calc trick. The pre-calc trick would be to compare the degrees of the numerator and the denominator. So the degree of the numerator is 2, and the degree of the denominator is also 2. So since the degrees match, where do we get our answer for this? The ratio of the lead coefficients. Yep. So you could just say equals 1/2. And if this were a multiple choice, I'm not going to pour over your work, and so you just circle the right answer, you move on, you're good, right? Okay, so let's try a different way. Let's say that it wasn't multiple choice, and you had to show some process. There's two other ways you could do this. Excuse me. Here's one way. You could check out the degree of the denominator, which happens to be x squared, right? It's degree 2. And here's what you could do. Oops. Here is where that pre-calc trick kind of comes from. You divide every single term by that degree that you found in the denominator. So it would be x squared over x squared plus 3 over x squared, all divided by 2x squared over x squared minus 1 over x squared. So if you just divide every single term through by that degreed variable, then you get a bunch of cancellations. So if you did that, you would get the limit as x goes to infinity, and here we go. This ends up being 1 plus 3 over x squared. And down here ends up being 2 minus 1 over x squared. And so now we can apply that little rule we talked about, where if the numerator is held constant and the denominator is getting gigantic, we're heading towards 0. So if you look at these two terms here and here, they both fit that category, right? Constant numerator, denominator being forced to get gigantic. And so that means this would go to 0 and that would go to 0, leaving us with 1 plus 0 and 2 minus 0. 1/2. Same answer. Good? Okay, so there's yet another way, and do you know what it is? Awesome, I get to show you something. Most of you have seen it before. So maybe it's totally out of context, right? This is like a final exam, it's the AP test, it's the whatever test, but it's not like the chapter 3 test. So you just look at this question, you're like, well, I don't know where this came from, but it's a question, so I'm going to try it. Maybe you look at it, and you think to yourself, well, if I kind of try like a direct substitution-ish kind of thing, if I go in the top, infinity squared, what's that? Infinity. And then you add 3 to that, just infinity again, right? So you're like, well, all right, that's interesting. So that's just an arrow. Okay, and then the denominator, gosh, infinity squared is infinity, times 2 is infinity, and what's minus 1 going to do? Not a whole lot. It's going to be infinity again. Huh, that's interesting. I'm getting way ahead of myself here, but this allows us to use L'Hopital's rule. Okay, and we're going to go back over this again when we get to chapter 8. So I'm just showing you 3 different ways to do this. So don't feel like, oh, I better know all 3 of them. At this point of the game, you really only have to know how to do one of them. I want to point something out here in a second. So don't shift into neutral. Like once you heard these guys say, hey, it's L'Hopital's rule, I remember that, or I don't know, maybe you've never seen this before. I'll prove this to you later. Don't worry. Please don't shift your mind into neutral, even if you did really good on this in AB, because I got something from the reading that's a little sneakily tricky, okay? So pay attention here in just a second. So because we got infinity for the top limit, infinity for the bottom limit, that allows us to use L'Hopital's rule. So you can then use it. So I usually just use a little arrow and an LH saying, hey, I'm going to use L'Hopital's rule. You can put LR for L'Hopital's rule, whatever. And so, Sean, just for your benefit, we'll prove this later. For now, just suspend any disbelief you might have. What we're allowed to do then is differentiate the top. You get 2x. There we go. And differentiate the bottom, and you get 4x. And you can retry the limit. So it's not the quotient rule. You just differentiate the top, and you differentiate the bottom. Well, this time when we retry our limit, don't we get essentially the same thing? 2 times infinity, that's just some other version of infinity. 4 times infinity, same kind of a thing. I didn't have to do it this way. I could have canceled my x's, but you didn't say anything, so I'm going to just keep going. I could do L'Hopital's rule one more time. So L'Hopital's rule for the second time would be the limit as x goes to infinity, and it would just be 2 over 4, which is 1/2. So the answer is 1/2. So that's a third way of doing it, right? You get to decide now. Right now, you get to decide, okay, I like this way better. I like that way better. And you just decide what you want to do. Later on, you will need to be able to do L'Hopital's rule really, really well. Now, can I give you a word of caution? And this was one thing that I did not know how much of a stickler they were on this. Can I show you how it is at the reading? Check this out. Let's say that this question was on the AP test last year. Okay, so just pretend with me. Let's say that this was your work. You with me still? Okay. And I don't know, maybe you put the little arrow with the LH, or maybe you didn't. But you showed the condition was met, right? Infinity over infinity. That's a for sure, right? So then we differentiate. Goodness, is my palm touching this? I don't know what the deal is. Oops. How about 2x over 4x? And then maybe we cancel out the x's, reduce. We end up with that. With me? That look pretty good? So this would have gotten only partial credit. No, you don't have to write, I use L'Hopital's rule, or you don't have to, that's fine if you do. That's kind of nice, but it's not a requirement. There's something up there that is very clearly a contradiction.
The equals infinity over infinity.
Yes. So look what I have here. I wrote this very specifically because I saw this about 1 million times as I was reading people's answers. I saw this. And then they did a nice job with L'Hopital's rule, and they end up with that. Isn't that a discrepancy? On the one hand, you're saying this limit equals infinity over infinity. And like 10 seconds later, you're like, no, hold on. No, it's equal to 1/2. See the discrepancy? So let's talk about what they expect you to do. Here are the variety of ways you could do this correctly and still get full credit. And avoid this little pitfall. You would have lost 1 point. So it's not like you would have just like totally lost all the points there, but watch what I'm about to do. Do you see the equal sign, the very first one? Here's what they were okay with this. Arrow does not mean equals, does it? It just means, and my next thought is, whatever, right? So by replacing the equal sign with an arrow, if that were your answer, you would have gotten full credit. You would have not lost that point. To me, that's the easiest way. Some other ways, like if you would have put, because you still showed that you met the condition for L'Hopital's. Pardon me for getting way ahead of myself. I just thought I'd say this now, and I'll say it again later, because I'm sure there's plenty of my students last year that probably missed that point, because I didn't make a very big deal about equals versus arrows and all that kind of thing. So I figure I'll make a little bigger deal here. 1 point is 1 point, right? If you see it again, hopefully you'll do fine. You also could have done this to show that you met the conditions for L'Hopital's rule. The limit of a quotient, is equal to, man, I am really struggling. There we go. Limit of a quotient is equal to the quotient of two limits. So you could have said the limit as x goes to infinity of x squared plus 3 equals infinity. So you've shown that the top goes to infinity. And then you could have said, well, I get the exact same thing when I do the bottom limit. So 2x squared minus 1, and that's also equal to infinity. So that, again, shows that you met the conditions for L'Hopital's rule. But you didn't say that the overall limit was equal to infinity over infinity. This is a frustrating one for me, because this like almost goes all the way to saying the thing that they weren't happy with, right? But they were okay with saying, hey, if you split it up and show the two parts, you're not really saying that the whole limit is infinity over infinity. And it's like, yeah, maybe. I kind of like the arrow thing, because the arrow is just saying, hey, here's my thought, and this is allowing me to then use L'Hopital's rule. So anyway, we'll talk about that for real when we really get to L'Hopital's rule and do, a little proof of it, that kind of thing. I just thought I'd say that right now. Good? Awesome. All right, fantastic. So number 2, I showed you 3 ways. From here on out, let's just be efficient. You see number 2. What do you, just you personally, what do you think would be the most efficient way to do number 2 if it were a multiple choice? So what does the degree trick tell you here? So in a multiple choice, I would hope that it would take you exactly that long. So don't feel like you're cheating or anything like that. Just use all of the little tricks up your sleeve, especially in a multiple choice. Call it good, move on, something different. Okay, let's move on ourselves to the other ones. There's number 3 and number 4. So check out number 3. Again, feel free to do the degree trick, although the degree trick does sort of fall apart somewhat on number 3. You might want to use the divided by the degree. And then we can talk about number 4 as well. So try number 3 just for the moment. You look at the degrees, and the degree of the top is bigger than the degree of the bottom. So in pre-calc, what did that trigger for you? What were you supposed to do?
It does not exist, or infinity.
So, but could it be negative infinity or positive infinity? I mean, it's kind of hard to tell maybe right away. Weren't you supposed to divide, and then that would lead you to some kind of an asymptote, maybe a slant asymptote that would take you to either negative or positive infinity? Yeah? That's what you could do, even if that's not what you did do. So what ultimately did you decide? I mean, Lenny kind of laid it out there. He's like, I think it's either positive or negative infinity. What did you decide? Negative infinity? Okay. So let's confirm that with a little process, because if you do have time and you are taking a test or a quiz and you're like, oh, I think it's probably negative infinity and I've got a couple reasons, but I want to be for sure, we could always do the degree trick, or not the degree trick, but the division trick real quick. So you could go limit as x goes to infinity, and can we just do this mentally? I'm going to divide everything through by x to the first. So if I do that, I get 3 over x minus 2x over 3 minus 1 over x. As I try to evaluate that limit, that would essentially give me negative 2 times infinity, which is negative infinity, over 3 minus 0. And really, what's the 3 going to do?
Nothing.
Nothing. So we end up with negative. I'm struggling with my infinities again today. There we go. Negative infinity. So Lenny, nice work.
What would happen if you said doesn't exist?
So it doesn't exist certainly applies here, right? Because infinity or negative infinity is not a real number. So if it was a free response, I would definitely take either, and so would the AP folks. If it was multiple choice, odds are pretty strong that the correct answer selection would be negative infinity, and one of the distractors would not be DNE. They're not going to give you both, unless they want you to fight them, because that would just not be very nice. Okay, we good? Okay, number 4. Number 4 might look out of place. You might be thinking, hey, I thought we were talking about limits and infinity and stuff, and all of a sudden it starts talking about horizontal asymptotes. Why would this be in this section of questions?
Because it might level out.
Might level out, and you said what, Darian?
Asymptotes are limits to infinity.
Yeah, like I would say horizontal asymptote is a way of describing the long-term limits, right? So yeah, so this really is limit as x goes to plus or minus infinity, depending on which direction we're trying to go. So if we're going to find these horizontal asymptotes, we technically are supposed to do this. Limit as x goes to infinity of 2x squared over x squared plus 4. And then also the limit as x goes to negative infinity of the same thing. So let's see here. You evaluate that first limit. What do you think is the most efficient way to evaluate that first limit? Yeah, degree trick, right? So the degree tells you that it should be 2. And what about the other one? This feels like a trick question, doesn't it? Feel free to investigate a little bit if you want, but what do you think? Everybody really wants to say 2, right? That would be very convenient. Is it really 2? You could do L'Hopital's. You could do the division trick.
It's 2.
It is 2. It is 2. So you do want to consider both. It's very possible to have 2 different asymptotes. And let's see here. I'm trying to remember what it was. There was a question about 7 or 8 years ago where there were 2 different horizontal asymptotes, and folks, pretty much everyone only considered the positive infinity behavior, and so like 98% of the people that took the test missed it, so they actually threw the question out. They didn't even count it. For whatever that's worth, in case you see something like that again, which I kind of have my doubts, you'd want to check both, just to be for sure. But this does work out to be 2 on both sides. All right, so that's that. Do you guys have any questions before we move on? Final topic of the day, I would believe. Think so? Yeah, probably. Okay, so let's take a look at it. Optimization. Optimization is essentially taking all the stuff we did in 3.3 and 3.4 and trying to apply it to somewhat real-world scenarios. So let's review some stuff here before we jump in. Optimization is another way of saying finding an optimum value or finding a blank or blank. Max or min, that's right. So optimization is about finding maxes and mins. And then a little canned statement from way back. I know with my folks, we said this repeatedly last year. Blank and blank occur at blank points or endpoints, blah, blah, blah. What do you think go on the first 2 blanks? Yeah, maxes and mins. Maybe this will help with the other ones. Occur at critical points or critical numbers, or endpoints if you do have a defined closed interval. And blank points are places where the derivative is blank or doesn't exist.
Critical and 0.
Critical and 0, you are correct. So just way of review, right? Just remembering all those things we learned in 3.3 and 3.4 and all of last year still apply here, of course. Okay, so just some strategies for optimization. A lot of times a picture is useful. You'll see me drawing a picture a lot. I know for me, visualizing is a good way for me to learn or organize my thoughts. I think that might be worth considering in a lot of cases. We want to try to identify the equation. Sometimes that's given to you. Sometimes it's pretty obvious. Other times you're going to have to work a little bit for it. Sometimes, I don't know, the word typically might be a little bit strong there. Sometimes you're going to have to use some substitution or some kind of algebra to get things workable for you. Consider realistic domain. Like you can't have -2 dogs in the yard or whatever. Just not possible. So we would reject any of those unrealistic numbers. And then use calculus, right? And by saying use calculus, what are the 2 methods that we have for finding and justifying relative extrema?
First and second derivative test.
First and second derivative test. If we're finding absolute extrema, we still find our critical numbers and we still find our endpoints, but then how do we organize and come up with a conclusion? We don't do a first or second derivative test, we do what? Yeah, plug it back into the thing you're trying to optimize, right? So you make like a little table or something and just compare outputs. So all those are possible. And just a note here, I think you remember this from last year perhaps. When we get into chapter 4, which is integration, we will definitely revisit these and kind of do like the full gas version of these. Right now, they're carefully selected to work with the things we've already talked about, but we'll come back around and do quite a bit with these in chapter 4. All right, so we're going to jump around a little bit, I think, just to make it as easy as possible for you. We'll skip number 1 for the moment. We'll come back to it. I think number 2 is a pretty nice one to start with. So number 2 says, on a given day, the flow rate, F, cars per hour on a congested roadway, is given by that equation right there. V is the speed in miles per hour. What speed will maximize the flow rate on the road? Very practical question. Someone who designs roads. So I heard it said over here pretty well that we do have a rate. I mean, F is a flow rate, but we are trying to maximize that flow rate. And so in order to find that, we need to recognize we need a critical number. In order to find a critical number, we need to find F prime and set it equal to 0. So did you guys all do the quotient rule, or did you flip up and do some kind of a convoluted product chain? You did a quotient? I think quotient makes sense. So let's see here. F prime would equal, well, low is pretty convenient. And so is D high minus high. D low, not as convenient, but it's not too bad. 0.04 V all over the denominator squared. So that's a nice step to have in there. Squared. Okay, so that's F prime. We want to find critical points, critical numbers. So we set that equal to 0. And this is where a little bit of knowledge goes a long way. What part of this do we not have to worry about at all when it comes to solving equals 0? The denominator doesn't matter at all, does it? It's all about the numerator. And so, if you want to mentally multiply that denominator over, or just get rid of it, or set the numerator equal to 0, it's the numerator that's going to make the whole fraction 0. So I just write something like 22, let's see here, this is going to be minus 0.04, so combined with 0.02 would be minus 0.02 v squared is equal to 0. And this is probably when you had to get your calculators right out to solve this. Yeah. Okay, so if you subtract and divide and square root, v is equal to what?
33.17.
3 decimals?
166.
166. Okay. So, hooray, we're done. We don't have to do anything else, right?
Yeah.
Yeah, we do. What have we found? We found, well, in terms of calculus, though.
The critical.
We found a critical point. Does a critical point guarantee that we have a maximum for flow rate? Because a critical point could generate a maximum, but could generate a minimum, and it also could generate an inflection point. Now, the hope here is that, since that's the only critical number we got, that would actually be the thing that would maximize flow rate. Otherwise, I wrote a pretty bad question, right? Because are there endpoints? Or maybe it's the endpoints. Should we think about endpoints? What would be the endpoints for V?
0 and
0, because speed can't be below 0. And what would be the upper end?
we don't know. We don't need the type of car, so
It's sort of open-ended, right? Because if someone could invent a car that goes like 185, then someone could probably invent one that goes 195, 205, 206. There's not really an upper end where, hey, this is the fastest a car could ever go. I don't think we can really say that. So I don't think there are endpoints to consider. So we need to hope that this is going to generate the thing we want it to generate. What could I use? How could I figure out if that really does produce a max for F? What could I use?
sign chart.
First derivative test with a sign chart, I think that makes the most sense. So make an F prime sign chart, and 33.166 goes in there. You could do a variety of test values, but one of them needs to be on the left side, and the other one needs to be on the right side, and we compare the sign change, and hopefully it's what we want. So did anybody do that? All right, Blake, what'd you get? How about that left interval?
Oh, I just put 30 and
30?
as my left interval, yeah.
30.
Yeah,
Okay, so when you plugged in a 30, what'd you get?
I just said it was positive because I could see it on the graph.
No, fair point. So if the calculator's active, then I think we'd assume you could use the technology. So, okay, I'm fair. That's fair. I'm fine with that. Okay, and then, so you said that was positive?
Yeah, so it was plus sign.
You could see it above the x-axis,
Yeah.
or you looked at the table or something. Okay. And then, of course, over here, you could try, do you guys try like 35 or 40 or something? 35? Okay, so f prime of 35, you check that out, and I'm assuming that that's negative something.
Yep.
So negative. And now that we've established those values, or at least we've looked at the graph and seen those values, now we can justify it, right? So you want to make sure that you are justifying it correctly, so you could say that f is maximized when v equals 33.166, because we've already proven this, but it's okay to say f prime of 33.166 equals 0, and f prime, capital F, I guess, prime, changes from positive to negative at that point, or at that v, at v equals 33.166. So we've proven it using the first derivative test. Anybody think about using the second derivative test on this one? Why not? Yeah, like another quotient rule with even more complicated top and bottom. It's not worth it. You're going to have to do some foiling or do a unpleasant chain rule in the midst of it. And so it's like, yeah, just do the first derivative test. This is not a time when second derivative test would be easier. So wise choice on your part. We good? Okay, good. All right, let's take a look then at example number 3 is a good one. So a farmer plans to fence a rectangular pasture adjacent to a river. Pasture must contain that many square meters to provide enough grass for the herd. What dimensions will require the least amount of fencing if no fencing is needed along the river? So this is a classic maximization, minimization type of a question. And this is also one where a picture would be wise. So start by sketching a picture.
I remember this one from last year.
We did one sort of like this one. You didn't like it?
No, it's hard.
We can do all kinds of things with fencing and rivers and walls and animals and things like that. So drawing a picture is definitely a good place to start.
It's an important question. What kind of animals are going to be inside the fence?
I'm going with llamas.
Okay.
Yeah, no cows this time, just llamas. So there's the rectangular pasture. You can see the river over there. We don't need a fence along that river. Yeah. So drawing a picture, getting a sense of what this is asking is a good first step. But somewhere along in here, we need to come up with an equation expressing the quantity that we're trying to, in this case, minimize, right? Because we're trying to minimize the amount of fencing he has to buy. So what could I write down that would express the amount of fencing that this farmer has to buy?
2x plus y equals a.
Okay, so let's see here. So based on that, I would say this is x and this is y. Is that what you were thinking? So we do have to label our picture in some way. He's labeled it backwards of the way that I would, because I would think x-axis horizontal, but it really makes no difference, does it? So I'm fine with that. And he said P is equal to 2x plus y. P, like the idea of a perimeter, the fencing perimeter.
Right.
Yeah, that makes sense.
For the amount of fencing.
You could put F for fencing or something, A for amount. I mean, I would say the variables just need to have meaning to you, and if they do, then I think you'll be able to work with them. So this is where something interesting happens, because if you say, hey, great, awesome, we have this equation for the amount of fencing, why don't I find P prime and set it equal to 0? This is where you're going to run into an issue. What is the issue you would run into?
2 variables.
2 different variables, yep. So we're not talking about like a 3-dimensional, like a space, something in 3 space, where you could have like partial derivatives and find slopes only in particular directions. We want to know just like the straight up regular derivatives. And so we can't really do that when we've got P in terms of 2 variables. We've got to break this down so that P is in terms of only 1 variable. McKenna, what could we use to help us do this?
Set it equal to like the 245,000.
Yeah, we need to use that too. So we'll use 245,000. Whoops. And how does that relate to what we've got up there? It does, right? Because 245,000 is an area. So yeah, I agree that that equals XY.
And then you solve for one of them, and then you plug it back in.
That's exactly right. Great strategy. So McKenna, since you started us down that path, what do you want to solve for?
Y.
All right, so that means divide by x. So y equals 245,000 over x. So we could write p equals 2x plus, and I'm going to rewrite it just slightly differently, 245,000 times x to the negative 1. That makes sense why we would do that? Because of what we're about to do? Yeah? You don't have to do that, but it's a good way to do it. Because the very next thing we're going to do, now that we have this really nice, beautiful equation that's all set up for us, if we're going to try to find a max or a min, we need to find, because we want to find critical numbers, right? So p prime, or you could call it dp dx if you wanted to. P prime equals 2 minus 245,000 x to the negative 2. Set that equal to 0. And I remember, like you guys mentioned, we did do something like this, or very, very similar to this. And most folks got the substitution okay. You know, it's like, yeah, I get it. And then the derivative was super duper easy. But then we got to this, and I was just like, now what? And it was kind of like, I don't know. So let's hear it. What do you think?
Take the derivative again.
No. We don't want p. Well, that might serve us well. Well, let me rephrase that. That might serve us well later. But as far as finding critical numbers, no, not going to help us. So what can I do? What's the algebra here? How do I need to solve for x, right?
So you can put the x squared on the bottom.
Okay, that's fair enough. So 2 minus 245,000 over x squared is equal to 0. That's fair. You can do that.
Add it over.
So add it over. Yep, so you're avoiding the issue like everybody else. 245,000 over x squared. But now I think it's unavoidable. What are we going to do?
Multiply both sides by x squared.
There you go. We need to get it out of the denominator, right? We don't want it there. So we're going to end up with 2x squared equals 245,000. And now we have something we can work with. We divide both sides by 2 and square root, and we get x, we get x is equal to what? 350. Yep, I thought it came out nice. So x is equal to 350. So again, is this the time where we say, fantastic, we're done for sure. We know this is exactly the right answer. Moving on. Not so much. I mean, I don't think this one does say justify your answer. It really doesn't. How could we be for sure that that actually does minimize the fencing? I think sign chart would work, no problem, but I think it's easier to use the second derivative test. Check this out. And this is where I was going with McKenna's idea earlier. I think she was just trying to get out of working with that negative exponent or something. But if we take that p prime and we differentiate it, wouldn't we get, let's see here, we would get p prime, or p double prime, excuse me, equals positive 490,000 x to the negative 3, right? Oh, I'm off the edge of my little screen there. I can see it here, but you can't see it up there. You believe me? X to the negative 3? Okay. And then you can just say p double prime of 350. And this you could actually do without a calculator. I mean, you couldn't get the exact answer, but couldn't you say for sure that if you plug a 350 in for x and put it under 490,000, we know beyond a shadow of a doubt, even if we don't know what the number is, that it's positive. Yeah, positive. You can use your calculator and figure it out if you want to. But we can say for sure that that is positive, because a positive divided by a positive is always positive. So if p double prime is positive, p is concave up, and so any critical numbers there would be minimizing p. So you could justify it using the second derivative test. You could debate me on that one. You might think, hey, I would rather do the first derivative test and make a sign chart. That's fine. That should work too. I just felt like doing a second derivative test was just a touch easier. That's just my opinion. Take it or leave it. So McKenna, is that as bad as you remembered it? The farmer in the field and the river? Okay. I'm glad to hear that. Okay, we solid? We good? So this next question, number 4, this will probably be our last one for the day, and we'll tackle the swimmer question. Number 1, we'll tackle that next time. But this one here, number 4, This is actually an old AP question that's been carefully manipulated to work for what we're doing here. It's definitely calculator active, but it's even though it's been manipulated a little bit, I think there's some really good principles in here that we could discuss, much of which is quite straightforward. So take a look here. We've got the tide removing sand from Sandy Point Beach at a rate modeled by that R function. A pumping station adds sand to the beach at a rate modeled by function S. You can see right there, R of t and S of t are both in cubic yards per hour. T is measured in hours. T equals 0. The beach contains 2,500 cubic yards of sand. This is actually a very appropriate time to be talking about a question.
So it looks like.
So like I said, the first bullet point
So it starts with this much and then it decreases.
is just wanting to know the net rate.
It only increases.
So did you guys do for number for the first bullet point? Did you guys do? Let's see here. S
And there's
of
no
4
between 0
minus R of 4.
There's no max value.
Because you got two different rates. One is,
Max
contributing to the amount of sand. The other one is taking away from the amount of sand. So you'd put the amount that is contributing to the sand to be a positive minus the one that is taking sand away. So when you ran that through your calculator, hopefully in radian mode, how did that end up working out?
Negative 1.908 or 109, yeah.
Negative 1.909?
Yep.
And that would be in cubic yards per hour. And so I didn't ask you this, but if I did say, let's interpret this, is the amount of sand increasing or decreasing at t equals 4? What would you say?
Decreasing.
Decreasing because the net rate is negative. Okay. And then for the next bullet point, what we would do to find out when the amount of sand is at a minimum, we would say S of t minus R of t. Again, that's our net rate. And that equals 0 because we're trying to find critical numbers of the amount function, if you will. So this is where the calculator really came in handy. Was there one or two critical points? Was it just one? Just one?
Just one.
Okay. So what was that critical point when you set S of t minus R of t equal to 0?
5.118.
5.118. And that's just using the zero finder on your calculator. And this is where having the calculator really, truly is handy because then can't you then immediately turn to the graph and be like, look, the net rate at that 5.118 goes from a negative value to a positive value. Therefore, that really, truly is describing a minimum. So justifying your answer, you would say something like that S of t minus R of t equals 0, like we already said, and it changes from negative to positive at t equals 5.118. Therefore, the amount of sand is minimized at that time. That make sense? Justification-wise? Now, what is the minimum value? We'd have to use a different tool to find out exactly what the minimum is. Do you guys know what that is? What? Math 9, also known as a numerical or a definite integral. We'll get to that stuff later. But for now, let's take a look at the final bullet point. At what time would y of t, the total number of cubic yards of sand on the beach at time t, be maximized? And the graphical region would look like this. If you graph S of t minus R of t, correct me if I'm wrong, but that graph looked, at least on the interval 0 to 6, looked something like that. Okay, so the only, oh gosh, sorry, that's right there on the little thing. You guys have a good representation in front of you? I'll try to use some shading to help with this. So the only critical number would yield a minimum, wouldn't it? So our critical number right there, that's not going to yield the maximum because that's where S of t minus R of t goes from negative to positive. So that can't be the max. So what are the only other candidates? They've got to be the endpoints. All right, so then you think about the endpoints. Which one is it? Is it going to be 0 or 6? And here's where you want to think about accumulating a certain net rate and how that's going to affect the amount. So if I start at 0 and I work my way to the right, all of this area is below the t-axis. So since it's below the t-axis, wouldn't that represent when R of t is bigger than S of t? In other words, the rate of sand leaving is bigger than the rate of sand coming in. So for that whole green area, wouldn't that be indicating that the amount of sand is decreasing the whole time? And then over here from that 5.118, whatever it is, to 6, that's where S of t would be bigger than R of t. So that little segment would be when the amount of sand is increasing. So what this comes down to really is comparing the size of areas. This is the best we could do at this point. So if you look at it, the area that represents the losing of sand compared to the area representing the gaining of sand is much bigger, right? And so that means over the course of 0 to 6, we've lost more sand than we've gained. Therefore, the max would have to be when t equals 0. So at t equals 0, and then the amount of sand would actually be how much?
2,500.
2,500, because it does mention that the initial amount was 2,500. So, and that would be, to give a graphical reason, honestly, there was an old question on some old AP test way back when. That's essentially what you had to do. You had to be like, well, the area below the x-axis was way larger than the area above, and that indicates that it would be the left endpoint that would be maximized, or the right endpoint was minimized, or whatever it was. But you had to use kind of a relative size of graphical stuff to justify it. So that's that. We'll tackle the swimmer question next time, but our friends